Hi, and welcome to The Dreaming Scientist, a quiet place in deep space with softly spoken science for your sleepy minds. Tonight we're going to talk about Venus, the planet that should have been our sister, but ended up as a warning label. Same star, same system, almost the same size, built from the same swirling disk of dust and gas as Earth. And yet instead of oceans and weather and life, it's a 460-degree pressure cooker wrapped in carbon dioxide and crowned with clouds of acid. Settle in, dim the lights, and get cozy. But before you do that, take a moment to like the video and subscribe to the channel. Also comment down below where you are watching from. It is always intriguing to know who is watching us from around the world. And thank you so much for being here. When the sun was young, it wasn't sitting in empty space with finished planets already in place. It was surrounded by a flat, spinning disk of gas and dust, the leftovers from the cloud that collapsed to make the sun in the first place. Inside that disk, everything was more or less the same raw material. Tiny grains of silicate rock, specks of iron and nickel, bits of carbon-bearing compounds, and some water locked up in minerals or ice, depending on the temperature. That disk wasn't two separate disks, one for Earth and one for Venus. It was one big shared feeding zone, and in the inner part of it, the part where the sun's heat kept things too warm for ices to stay as ice, little dust grains started bumping into each other, sticking and growing. As they grew, they started to feel their own gravity. Pebbles became boulders. Boulders became kilometer-sized planetesimals, and those started colliding and merging into bigger and bigger bodies called planetary embryos. Venus and Earth both formed right in that zone, right next to each other, eating from almost the same patch of space. That's why they're so close in size and mass. They had access to about the same amount of stuff. Both of them probably went through the same violent stage of getting smacked by big bodies. Both of them would have melted on the outside from all the impacts, separated into a dense iron core and a rocky mantle, and both of them would have started outgassing, that is, letting gases trapped inside come out to build their first atmospheres. In other words, Venus was not born bad. It was born as a perfectly normal inner rocky planet, exactly the kind our solar system likes to make. The only real, hard difference at this stage was distance. Earth ended up about 1 astronomical unit from the Sun. Venus ended up at about 0.72 AU. That doesn't sound like much, but the closer you are to the Sun, the more energy you get, and Venus gets almost twice the sunlight Earth does. That extra sunlight is the seed of everything that goes wrong later. It means Venus started off a bit warmer everywhere. Warmer surface, warmer early atmosphere, more evaporation if there was water, and on a planet, a bit warmer doesn't just mean you sweat more. It can mean you cross the line where your planet can't get rid of heat as fast as it's coming in. So, same kitchen, same recipe, almost the same cake pans. One of them was just baked too close to the oven door. A lot of people picture Venus as permanently hellish, like it popped out of the disk already drowning in acid at 460 degrees. That's unlikely. Early in the solar system's history, the sun was dimmer than it is now, and Venus, though closer, would have been getting less total energy than today. On top of that, when rocky planets first form, they release water vapor, carbon dioxide, nitrogen, and other gases from their interiors. Comets and wet asteroids can also deliver extra water. Put those together, and you can actually imagine an early Venus that had some liquid water on its surface. Maybe shallow oceans, maybe big lakes, maybe episodic seas depending on how often volcanism released steam. Climate models have even shown that if Venus had a decent amount of water and built up thick clouds on the day side, those clouds could have reflected enough sunlight to keep it temperate for hundreds of millions of years. That's important because liquid water is not just nice to have, it's the planet's main tool for cleaning up CO2. Water dissolves CO2, water makes rain, rain weathers rocks, weathering washes carbon into basins. On Earth, that's the start of our thermostat. So there's a picture. We can't prove it yet, but it's a real, worked-out scientific picture, where young Venus was a warm, maybe even pleasant planet with water, clouds, and active volcanism, kind of like a hotter Earth. But Venus's problem was that its margin for error was tiny. Even though the Sun was dimmer back then, Venus was still closer. As the Sun slowly brightened over hundreds of millions of years, which is what stars like ours do, Venus got pushed toward a dangerous edge. A touch more sunlight means a touch more evaporation. More evaporation means more water vapor in the atmosphere. Water vapor is a very strong greenhouse gas. It traps heat. Trapping heat makes the surface warmer, and that makes even more water evaporate. If you have oceans, you can get into a loop where warming makes vapor, vapor makes warming, and the planet can no longer radiate enough heat back into space to balance what it's getting from the star. That's the start of a runaway greenhouse. Earth sits far enough out and has enough cooling tricks that we've never tripped that wire. Venus, packed in tighter, couldn't back away. So even if Venus once had blue patches, clouds, and a water cycle, it was standing on a trapdoor the whole time, and as the Sun brightened, that door started to open. The phrase runaway greenhouse gets thrown around a lot, but on Venus it means something very specific and very ugly. A greenhouse effect by itself is normal. Earth has one, and without it, we'd be a frozen ball. Sunlight comes in mostly as visible light, gets absorbed by the ground and lower atmosphere, and the planet tries to re-emit that energy as infrared. Greenhouse gases absorb some of that infrared and send part of it back down, warming the surface. That's fine as long as the planet can still, overall, get rid of as much energy as it receives. A runaway greenhouse is when the planet can't do that anymore. On Venus, as the surface got warmer, more water evaporated. As more water evaporated, the air's ability to trap heat got stronger. As trapping got stronger, the surface got even warmer. At some point, adding more heat didn't increase the planet's ability to radiate it away. The atmosphere became so moist and so opaque to infrared that Venus hit an upper limit on how much energy it could shed to space. But the Sun kept delivering energy. So the only thing left to change was the surface temperature. It had to climb. As it climbed, all the surface water, the stuff that could have made rivers, oceans, weathering, was forced into the atmosphere as steam. High up, in the thinner, UV-bathed part of the atmosphere, that steam was easy pickings for sunlight to break apart. The hydrogen escaped to space. The oxygen got locked away. In other words, Venus boiled its own oceans into the sky and then lost them. And once the water was gone, the planet lost the tool that Earth uses to pull CO2 out of the air. So all the carbon dioxide that volcanism had been releasing and would continue to release started to pile up in the atmosphere. Water vapor triggered the runaway. CO2 built the final prison. Today, about 96% of Venus's atmosphere is carbon dioxide, with a surface pressure 92 times Earth's. That enormous CO2 blanket, sitting closer to the Sun than we are, keeps the surface at around 460 degrees Celsius everywhere, day and night, equator and pole. And because the atmosphere is thick and circulates fast, Venus can't cool off locally. There's no cold night side. There are no polar refuges. The greenhouse is global and permanent. That's why Venus is so scary as a climate lesson. It shows that if you push a terrestrial planet hard enough, More sunlight, more vapor, no way to bury carbon. You don't just get a bit warmer. You get a switch into a totally different mode, a mode that doesn't have an easy way back. Earth can warm and cool over millions of years because it has a built-in brake, the carbon silicate cycle. CO2 in the air dissolves in rainwater, rain weathers rocks, the products wash into the ocean, carbon gets locked in sediments, and plate tectonics eventually drags that carbon down to be recycled. If the planet gets warmer, weathering speeds up and pulls more CO2 out. If it gets cooler, weathering slows and volcanic CO2 can build back up. That's a thermostat. Venus had the same ingredients for the start of that cycle: volcanism to give it CO2 and water, fresh hot rocks to react with. But when the runaway greenhouse shoved all its water into the sky and the sun split that water, Venus lost the one part of the mechanism that really matters: liquid water on the ground. No water on the ground means no rain. No rain means no large-scale weathering. No weathering means no steady transfer of carbon from the atmosphere into long-term storage in rocks. On top of that, Venus doesn't seem to have plate tectonics like Earth. Its outer shell looks like one big stiff lid, not a bunch of sliding plates. Without subduction zones, you don't get to bury carbonates deep in the mantle. So picture what happens after the runaway. The planet is hot, the surface is dry, the atmosphere is already thick with CO2, and volcanoes are still doing their thing, releasing more gas. On Earth, a burst of volcanism makes the air richer in CO2 for a while, but the oceans and weathering catch up. On Venus, a burst of volcanism just makes the air richer in CO2 forever, because there's nothing in the system to pull it down again. That's why Venus's atmosphere is so huge today. It's not just that it ran away once, it's that after it ran away, the drawdown mechanisms were gone. You can think of it like this: Earth and Venus both had a faucet and a drain. Venus heated up so much that the drain rusted shut, but the faucet never turned off. Every molecule of CO2 that came out after that was one more blanket on a bed that was already too hot. And because Venus sits closer to the Sun, the energy constantly pouring into this broken system kept the lower atmosphere hot enough that surface minerals couldn't even help out much. Many of the reactions that would lock up gases work best at cooler temperatures. So Venus became a planet where the atmosphere is the main actor, not the surface. The surface can't fix the air because it's too hot and too dry, so the air just gets to stay king. That is the core difference between us and our burnt sibling. We kept our drain, Venus didn't. On Earth, the atmosphere is a film: thin, delicate, easy to disturb. On Venus, the atmosphere is the planet's personality. It is massive, it is deep, and it controls everything beneath it. Today, Venus's air is about 96% carbon dioxide, a few percent nitrogen, and then trace acidic stuff like sulfur dioxide that goes on to make sulfuric acid droplets in the clouds. At the surface, the pressure is about 92 bars. That's like being a kilometre under Earth's ocean. And the temperature is 460 degrees Celsius. You could put the same stove on full power at the surface of Venus, and it wouldn't get anything hotter. Because the atmosphere is so heavy and so good at trapping heat, it smooths out temperature differences. Day, night, equator, pole. It's all basically the same furnace. Up high though, around 50 to 70 kilometers, it's cooler and more pleasant, which is where the thick, bright cloud deck lives. Those clouds are mostly tiny sulfuric acid droplets constantly forming and falling and reforming, and they're the reason Venus looks so brilliant from Earth. But those pretty clouds don't save the surface, they sit too high. Below them, infrared radiation from the hot ground just bounces around inside the thick CO2 blanket. Another strange thing happens because the atmosphere is so dominant. It moves faster than the planet spins. Venus itself rotates slowly and backwards, but the atmosphere at cloud top level super-rotates, whipping around the entire planet in just a few Earth days. That fast flow helps spread solar heating evenly, which is why Venus doesn't cool off on the night side. It's like sitting in an oven with a fan. That super-rotation is powered by the contrast between the day side and night side, and by the way solar heating is absorbed at different layers. Add in Venus's slow rotation, and you get a system where the air can basically ignore what the ground is doing. That's a big clue about the climate history. Once the atmosphere got this thick and this dynamic, the surface lost control of its own temperature. You can't cool a patch of ground when the air above it insists on staying hot and replacing itself constantly. You can't build ice caps. You can't have seasons that matter. You can't build a water cycle. You have a single, planet-wrapping, self-reinforcing climate state. And because sulfur is present high up, we know something, probably volcanism, is still feeding the system from below. So the atmosphere isn't just a leftover of a past disaster. It is an active, layered, acidic, fast-moving machine that keeps Venus in the very state that made it. On Earth, the surface tells the sky what to do. On Venus, the sky told the surface, "You live like this now." Venus doesn't just spin slowly, it spins weirdly, slowly. One rotation takes about 243 Earth days, and it goes in the opposite direction to most planets. That means a solar day on Venus, noon to next noon, is shorter than its rotation because of its orbit. But for the climate, the key fact is, the solid planet turns so lazily that the atmosphere basically laps it over and over. On a faster spinning planet, the Coriolis effect breaks the atmosphere into bands, helps set up day-night differences, and generally makes it harder for the air to just smear heat everywhere. On Venus, the slow rotation and the intense solar heating at the top of the atmosphere help drive that super rotation we talked about. Winds at the cloud tops can go 60 times faster than the surface. That means any attempt by the surface to cool, say during its long night, just gets cancelled by hot air arriving from the day side. The slow spin may even have helped Venus get into the runaway in the first place. Some climate models show that slow rotators can build huge, thick clouds on the day side that reflect sunlight, which sounds good, but they can also set up very strong vertical motions that trap heat below. And once Venus lost its water, clouds became mostly acid, not water, changing how reflective and how stable they were. The slow rotation also matters for the interior. Fast rotation helps power planetary dynamos by stirring liquid metal cores. Venus's crawl means less help from rotation, which is one reason it doesn't have a strong global magnetic field. No strong field means the solar wind can interact more directly with the upper atmosphere, and that's where we get to the second punch. Once Venus put its water up high, that water was exposed to UV and to a wind that could help sweep the light hydrogen away. So the slow spin is tied to two of Venus's biggest problems. It let the atmosphere dominate the temperature everywhere, and it helped make sure Venus never built the magnetic shield that could have protected what was left of its water. It's a neat example of how a thing that looks innocent, how fast a planet turns, can have knock-on effects all the way from the core to the clouds. Earth's 24-hour spin helps mix heat, helps drive weather, and together with our core structure, helps run our magnetic field. Venus's 243-day crawl gave the atmosphere time to wrap around the planet and gave the Sun an easier target. That's why we keep saying, Venus didn't fall apart because of one big flaw. It had several small disadvantages: closer to the Sun, slower spin, weaker field, no plate tectonics, and when the runaway greenhouse hit, those disadvantages all lined up to keep it hot. Earth leaks its internal heat politely. Our crust is broken into plates that dive under one another. We have a mix of mid-ocean ridge volcanism and arc volcanism, and the whole thing keeps the mantle from getting too backed up. Venus doesn't seem to have that safety valve. Its outer shell looks like one big, mostly unbroken lid. If you keep pumping heat from the interior up against a lid that doesn't move, sooner or later the lid weakens in places and the interior finds a way out in bigger, more dramatic episodes. That's what Venus's surface looks like. Huge volcanic plains that seem to have flooded across older terrain. Those big round coronae that look like mantle plumes tried to push up and then sagged, and a crater population that is suspiciously uniform. If a surface has been collecting impacts for billions of years, you see older areas with lots of craters and younger areas with fewer. On Venus, the distribution makes more sense if a very large fraction of the surface was reset in a relatively short geological time, sometimes called catastrophic resurfacing. Imagine hundreds of thousands or millions of cubic kilometers of lava pouring out over a few tens of millions of years, burying old craters, releasing gas, making the planet look younger than it actually is. That's not just a cool geology fact, it matters for climate. Every big resurfacing episode would have belched out more CO2 and more SO2 into an atmosphere that, by then, had no ocean and no rain to take it back down. On Earth, even supervolcanoes can't wreck the climate forever because water and rock chemistry slowly mop up after them. On Venus, a resurfacing episode is more like turning up the sauna and throwing more water on the coals, but the steam has nowhere to go. This also means Venus's climate may not have been perfectly steady over the last billion years. It may have had pulses, times when the atmosphere got even thicker in sulfur compounds, times when the cloud deck changed, times when the already high surface temperature ticked up a bit more. Newer studies even suggest there may be spots on Venus today that look like they've changed recently. Hints of active or at least geologically young volcanism. If that's right, then Venus is not a frozen disaster. It's a disaster that still twitches. And that fits the stagnant lid picture beautifully. No plates, so heat builds. Heat builds, so the lithosphere weakens. Lithosphere weakens, so magma erupts. Magma erupts, so greenhouse gases are replenished. It's a loop with no negative feedback in it. This is one of the big things we want the next Venus orbiters to pin down. How often did resurfacing happen? How thick were those flood lavas? And is any of it still going on now? Because the more often Venus has resurfaced, the more times it has reinforced its own hell. To really see what went wrong on Venus, you have to put it right next to Earth and compare line by line. Both are about the same size, so both should have started with hot interiors and the ability to hold atmospheres. Both formed from similar material, so both should have outgassed water vapor, carbon dioxide, nitrogen, and sulfur compounds. Both got hit a lot in the early solar system and probably had magma oceans. That's all the same. Now the differences. Earth is farther from the sun, so it started a bit cooler and had more headroom as the sun brightened. Earth either kept or was supplied with a lot of water early, so it very quickly had oceans, big ones, that could absorb CO2 and run a water cycle. Earth's interior and 24-hour spin let it build a strong magnetic field, so its atmosphere was better shielded from the solar wind. Earth developed plate tectonics, which meant it could take carbon from the atmosphere-ocean system and bury it in the mantle through subduction, then release some of it back in a controlled, slow way through volcanism. And Earth evolved life, which over time started changing the chemistry of the air, adding oxygen, making soils, speeding up weathering. Venus, closer in, so warmer, likely had less time with surface liquid water before the sun pushed it over the edge. lost its water to the upper atmosphere where UV could break it and the solar wind could erode it, lacked global plate tectonics, so it couldn't bury carbon, lacked a strong magnetic field, so it couldn't shield what little water remained, kept erupting, so it kept adding CO2. That sequence makes Venus the no-breaks version of Earth. Everything Earth did to stay habitable — oceans, weathering, recycling, shielding, biology — Venus either couldn't do or couldn't keep doing. That's why you don't get a halfway Venus. You don't get a bit too warm, but still okay. Once you lose the water and the recycling, the climate runs to the hot end and stays there. And that's the punch your viewers should walk away with. Just changing the distance to the Sun by a few dozen million kilometers in the inner solar system is enough to separate a living planet from a dead one, even when both started the same. That makes Earth's position look a lot less casual. For a planet that shines in our sky almost every clear morning and evening, Venus is still surprisingly mysterious. We don't know exactly how long it had liquid water, or how deep that water was. We don't know precisely when the runaway greenhouse locked in. Was it very early, when the sun was still dim, or did Venus manage to hang on to a warm, cloudy, maybe even rainy climate for 1 billion years before tipping? We don't know how often those resurfacing events actually happened, or whether they were truly global wipe and recoat episodes, or more like scattered massive eruptions over time. We don't know how fast Venus is still losing gases to space today, or how variable its sulfur dioxide output is over decades. And we don't know its deep interior well. Is the core still molten? Is there any kind of sluggish convection that could, under different conditions, have made a magnetic field? All of those unknowns aren't just trivia. They're the keys to telling whether Venus is a planet that went bad fast, or a planet that slid slowly down a slope it couldn't climb back up. That timing matters for exoplanets. If Venus fell early, then rocky planets this close to Sun-like stars may have very short, nice windows. If Venus stayed good for hundreds of millions of years, then even inner rocky planets might have had decent surface conditions for a while. That changes how we think about where to look for ancient biosignatures in other systems. And the unknowns matter for climate physics too. Venus is our only real-world high greenhouse laboratory. If our models can reproduce its temperature profile, cloud structure, and circulation, we can trust those models more when we push them to extremes. If they can't, it means we still don't fully understand how thick atmospheres with strong solar heating behave. And that's important even for Earth, because Earth's atmosphere could, in the deep future, get thicker and warmer as the sun brightens. That's why the upcoming Venus missions are such a big deal. They're not just more data, they're the missing chapters we need to make the Venus story tight enough that you can narrate it confidently, start to finish. Right now we tell parts of it with probably and models suggest. After those missions, we hope to tell it with Venus was wet until, and Venus resurfaced around, and Venus is still venting here. That's the difference between a cool space story and a useful planetary lesson. Whenever people hear runaway greenhouse and Venus, their brains try to jump straight to, is that what's going to happen to Earth? So let's nail that down clearly, slowly, and with the right weight. Venus is what happens when you take a rocky planet that's almost Earth's size, put it noticeably closer to the Sun so it gets a lot more energy, let it warm until its water is mostly in the sky, and then let the Sun and the solar wind steal that water so it can never come back down. After that, you let volcanism keep adding CO2 to an atmosphere that has no oceans, no rain, no plate tectonics, no biology, to pull it back out. That is a different situation from Earth's. Earth sits farther out, So we started with more wiggle room before sunlight pushed us toward any kind of runaway. We also kept huge oceans, which are a massive heat sink and a massive CO2 sink. We run plate tectonics so we can hide carbon in the mantle. We have a magnetic field so the sun can't easily strip our top atmosphere. And we never got to the point where most of our water vapor was up high getting fried. That's why Earth has had liquid water for billions of years, even as the sun slowly brightened. So no, Earth is not about to turn into Venus. But, and this is the real use of Venus, it shows that the physics of an unstoppable greenhouse is not made up. We have a real, full-scale, badly overcooked example right next door. That helps in two ways. First, for climate science, if we can make a model reproduce Venus's insanely hot surface, thick CO2 atmosphere, and sulfuric acid cloud structure, then we know our radiative transfer and convection physics are solid even at extremes. A model that can match Earth and Venus is a model we can trust more. Second, for public understanding, Venus teaches that a planet's ability to undo warming depends on what tools it has: water, weathering, tectonics, distance. If you lose the tools, warming can become one way. We still have the tools. Venus doesn't. So when you tell this on your channel, the smart way to frame it is, Venus is not our forecast, it's our boundary condition. It shows one end of the dial. It tells us that if you push a terrestrial planet hard enough and strip away its coolant, you don't get a gentle new climate, you get a locked inferno. That makes our current situation on Earth feel more serious without being dramatic. We are doing something real to our atmosphere, and we know what the extreme version of that looks like because the solar system already ran that experiment 0.28 astronomical units closer in. It also helps cut through the lazy habits some people have of saying planets always recover. No, sometimes they don't. Venus didn't recover. Venus shows that you can reach a point where the planet itself cannot climb back down. The reason we can is because we didn't throw away our water, we didn't shut down our recycling, and we're not sitting too close to the heater. That's the nuance a sleepy science video can actually land, because you have time to say it without shouting. Now that we've found thousands of planets around other stars, we keep seeing headlines that say things like, Earth-sized planet discovered in the habitable zone, and people quite reasonably imagine blue oceans and green continents. Venus is the reason we have to be stricter than that. By almost every dumb first-pass metric, Venus would look promising from far away. It's about Earth's radius. It orbits at a distance from its star that, depending on how generous you are, isn't that much closer than Earth. It's clearly rocky. It clearly has an atmosphere. If Venus were orbiting another star and we saw it transit, the press release might call it a potentially rocky, temperate world. But we live here and we know better. Venus is not temperate, it is not moderate, it is not wet, and it is not friendly. That means Earth-sized is not the right filter. What matters is energy in and energy out, and what the planet can do with water and carbon. Venus gets too much energy in, can't get enough out, lost its water, and couldn't bury carbon. So when we point our telescopes at other stars and we see a planet that is Earth-sized but close to its star, especially if the star is active, we should expect a Venus analogue far more than we should expect a second Earth. Astronomers now literally talk about a Venus zone, the region around a star where a terrestrial planet is likely to end up hot, waterless, and CO2 choked, even if it was born with water. That's Venus's scientific legacy. It drew a line for us. And this is where Venus helps your audience think sharper. Lots of exoplanets will look exciting in thumbnails, but many of them will be bright, cloudy ovens. A thick, reflective cloud deck can make a planet look cool in visible light while hiding a furnace underneath. Venus proves that. So the safe way to talk about Earth-like worlds is to say, same size is not enough, same star is not enough, roughly similar orbit is not enough. You need to know, did the planet keep its water? Does it have a way to trap or bury CO2? Does it have any kind of shielding from its star's wind? And is it sitting outside the Venus zone? If you can't answer those, you don't get to call it another Earth. That's the quiet, grown-up lesson Venus gives us. Even in the same system, two almost identical beginnings went in opposite directions. Why would distant systems be simpler? Whenever people really get the Venus story, that it was kind of like us and then it cooked itself, the next thought is, well, could we cool it down? It's a natural sci-fi impulse, but once you walk through the actual state Venus is in, the answer gets pretty brutal. First, the atmosphere. Venus doesn't just have a lot of CO2, it has the planet's mass worth of CO2 sitting on it, 90 plus bars. On Earth, our whole atmosphere is 1 bar. To make Venus pleasant at the surface, you'd have to get rid of the bulk of that gas. There is no natural ocean waiting to dissolve it, no cold pole to freeze it, no plate tectonics to bury it. You'd have to either bind it chemically, which would require unimaginable amounts of material, or lift it off the planet, which is even worse. Second, the temperature. The ground is hot enough to melt lead. Even if you put up a giant sunshade in space to reduce the sunlight hitting the top of the atmosphere, you'd still have to wait a very long time for that thick atmosphere and hot surface to cool, and during that time, the planet would still be putting out sulfur compounds and maybe new CO2 from volcanism. Third, the water. Venus doesn't have oceans hiding underground that would just reappear once it cooled. The hydrogen from that water is gone, lost to space. You'd have to import water in planetary amounts and then protect it from being stripped again. And fourth, the magnetic field. Because Venus doesn't have a strong global field, the upper atmosphere is always more exposed to the solar wind than Earth's. So even if you somehow cooled the planet, shrank the atmosphere, and delivered water, you'd still have to deal with the fact that the star can take it away again. That's why planetary scientists usually talk about habitats in the Venus atmosphere instead of terraformed Venus. Up in the 50 to 60 kilometer layer, the pressure and temperature are fine, and the thick atmosphere actually shields you from radiation, so you work with the planet, not against it. The deeper lesson, which suits your channel, is this. Some planetary states are reversible and some are structural. Mars' thin atmosphere could be thickened, Titan's hydrocarbons could be managed. Venus's current state is structural. It is the endpoint of too much sun and too little water. A planet that dried itself and then kept belching greenhouse gas has locked itself in. That's why Venus is a warning, not a project. A lot of people think of a planet's habitability as a yes, no thing. Can you live there right now? Venus shows us we have to think in time slices. Early on, when the sun was dimmer and Venus maybe had clouds and surface water, Venus might have been marginally habitable, or at least friendly to liquid water. As the sun brightened and Venus got pushed into a runaway greenhouse, it crossed a threshold. After that, not only was it uninhabitable, but it was on a path where it would get more uninhabitable with time, because volcanic outgassing would keep thickening the atmosphere and the sun would keep getting brighter. Earth, by contrast, has managed to stay inside its habitable window while the sun brightened. It did that by drawing down CO2, by circulating its interior, by using water and life to change its atmosphere. In other words, habitability is not just are you in the right place, It's, can you stay in the right place while your star changes? Venus couldn't. That's a huge lesson for exoplanet work too. If you see an Earth-sized planet around a star that's older than the Sun, sitting as close as Venus sits, you should suspect it has already done what Venus did. If you see one around a very young star, maybe it's still in its pleasant phase, but it might be a temporary pleasant phase. Venus tells us planets can have habitable youth and uninhabitable adulthood. It also tells us that the inner edge of the habitable zone creeps outward as the star brightens. Earth will one day face the same slow squeeze Venus already lost to. That makes Venus a kind of time mirror. Looking at it, we can see one way in a planet's end. That's an excellent sleepy science point to make. Not all planets get to be nice forever. Some of them start okay and drift into bad. Some of them, like Venus, drifted faster. Some of them, like Earth, linger longer. And the difference can be just a few tens of millions of kilometers. If you only ever think of Venus as the hot planet, you miss one of its weirdest twists. The best place for humans on Venus is not the ground, it's a band of sky about 50 to 60 kilometers up. Down on the surface, everything is lethal. 90 bars of pressure, 460 degrees Celsius, carbon dioxide everywhere, corrosive stuff in the air, and light that has been filtered through thick clouds. But climb in your mind through that heavy air and you reach a level where the pressure drops to about 1 bar, the same as Earth's sea level. And the temperature is just a warm day. The winds up there are fast but smooth because they are part of Venus's super-rotating atmosphere that laps the planet in a few Earth days, even though the solid planet crawls. That layer sits inside the global cloud deck made of sulfuric acid droplets, which is why any real vehicle would have to resist acid, but as far as pressure and heat go, it's surprisingly friendly. You can even float in it using Earth-like air, because Earth air is lighter than Venus air. That's why some mission concepts talk about floating labs, or even floating habitats instead of long-lived landers. And for science, that band is gold. It's where you can best sample how much sulfur is coming up from below, how the clouds are forming and raining acid down, how fast the atmosphere is circulating, and how energy is moving from the lower, hotter layers to space. That tells us whether Venus is still being fed from the inside, which tells us whether it's still reinforcing its own greenhouse even now. So even Venus, the failure case, has a balcony where we can stand and watch the crime scene without dying in minutes. That's such a Venus thing, same ingredients as Earth, but stacked upside down. Venus didn't just make one bad atmosphere and retire. Everything we've seen of its surface and skies points to a planet that kept releasing gas from its interior after it was already too hot to clean it up, which is exactly the worst thing a planet in Venus's position could do. When Magellan mapped Venus with radar, it didn't find a surface covered in ancient battered highlands like the Moon's. It found enormous volcanic plains, long winding lava channels, pancake-like domes, and odd circular features called coronae, which look like places where hot mantle pushed upward and deformed the crust from below. That is the fingerprint of a world that doesn't have plate tectonics to bleed heat steadily, so it stores heat under a stiff outer shell and then dumps a lot of it in bursts. Every one of those dumping events would have released new gases, carbon dioxide and sulfur dioxide especially, into an atmosphere that no longer had rain, oceans, or subduction to bury them. On Earth, a big eruption adds CO2 to the air, but long-term weathering, oceans, and plate motions gradually take it back out. On Venus, a big eruption adds CO2 to the air and it stays there. The same goes for sulfur. Volcanic SO2 on Earth can make sulfate aerosols that rain out. On Venus, it's lofted into the upper atmosphere and turned into sulfuric acid, thickening the cloud deck that makes Venus bright but doesn't cool the ground. Later missions even saw hints that this is still happening. Venus Express saw sulfur dioxide levels at the cloud tops change over just a few years. That's hard to explain unless fresh gas is coming from below. Some reanalyses of Magellan data suggest vents have changed shape, as if material collapsed or new lava was emplaced. If that's confirmed by the next generation of orbiters, it will mean Venus is not just a fossil of a runaway greenhouse. It is an active runaway greenhouse, still slowly topping up the blanket that cooked it. That turns the Venus story from long ago it made a mistake into it never stopped making the same mistake. And it deepens the lesson for Earth and for exoplanets. If a rocky world loses its water and its carbon sinks, then ordinary, healthy planetary behavior, interior heat rising, magma forming, gases venting, becomes deadly because every breath from inside goes straight into an atmosphere that has no drain. Venus's volcanism is not a side note. It's the engine that kept the prison door locked. The runaway greenhouse pushed Venus's water into the sky, but it was the sun, plus Venus's lack of a strong magnetic shield, that made sure that water was gone forever. Here's the sequence in plain English. Once the surface got hot enough and the greenhouse thick enough, water that had been liquid, lakes, shallow seas, even just surface moisture, was forced to evaporate. That water vapor didn't just stay low down, some of it rose into the upper atmosphere, where the air is thinner and more exposed to the sun's ultraviolet light. UV light is energetic enough to split water molecules into hydrogen and oxygen. Hydrogen is very light. If you give those hydrogen atoms a bit more energy, from sunlight or from the charged particles of the solar wind, they can reach speeds that let them escape the planet's gravity altogether. Oxygen, being heavier and chemically grabby, tends to get stuck. It can react with surface rocks, volcanic gases, or other atmospheric species. Over millions and then billions of years, that process acts like a ratchet. More water gets lofted, more hydrogen escapes, the total water inventory shrinks. On Earth, two things make that less of a problem. We sit farther out, so less of our water column is hanging up high in the danger zone, and we have a strong global magnetic field generated by our fast rotation and liquid outer core. That field forces most of the solar wind to go around us. Venus spins slowly, and as far as we can tell, doesn't run a comparable dynamo, so it meets the solar wind more nakedly. It does form an induced magnetosphere. The solar wind drapes around its ionosphere, but it's weaker and leakier. That makes it easier for the sun to strip off light particles. The proof is in Venus's present-day atmosphere. It has a very high ratio of deuterium, heavy hydrogen, to normal hydrogen. That's exactly what you expect if the planet once had a lot more water and lost the normal hydrogen faster than the heavy stuff. So the full story is, Venus warmed, put its water in the sky, had no magnetic umbrella, and sat close enough to the sun that its water got broken and its light half got stolen. After that, even if volcanism released more water from the interior, it would face the same fate. Up, broken, gone. That's why we say Venus isn't just hot, it's dry beyond repair. Cooling it wouldn't magically make oceans reappear, because the hydrogen part of that water is in space now. And that's the sharp exoplanet lesson. A rocky planet that's too close to its star and doesn't have a good magnetic field can lose its oceans even if it started wet. Earth size doesn't save you from the star if you cook your water into the high atmosphere. One way scientists test their ideas is by asking, what if we nudge one thing? So people have run Venus-like planets in climate models with slightly different rotation rates, starting water amounts, cloud behaviors, or stellar brightness. Some of those experiments show that a faster spinning Venus could have built thick reflective clouds over its day side that would have bounced more sunlight back to space and delayed the runaway. Others show that if Venus had started with a truly huge amount of water, it could have kept surface liquid for longer by powering more weathering. A few even suggest that with the right combination of clouds and rotation, a planet as close as Venus might have been habitable for a good chunk of time when the sun was younger and dimmer. That's useful, because it tells us Venus didn't become hell because of a single unavoidable law. It became hell because its specific set of parameters all leaned the wrong way. Closer to the sun than Earth, so it got more energy. Slower spin, so its atmosphere could wrap around the planet and erase temperature differences. No long-lived magnetic field, so once water was aloft, the sun could strip it. No plate tectonics, so it couldn't bury carbon. Continued volcanism, so it kept adding greenhouse gas. Change any one of those a lot, make it spin faster, give it more water, move it a bit farther out. And you could imagine a Venus that limped along as a steamy, cloud-shaded world instead of racing into the oven. That matters when we look at rocky worlds around other stars. We already see planets that are tidally locked, planets bathed in strong flares, planets hugging dim red dwarfs. Without Venus, we might optimistically label some of them warm Earths. With Venus, we know better. Some of them will be cooked Venuses. Our Venus is simply the version where every shove was in the same direction, toward heating, drying, and trapping. That's why the story is so clean to tell. It's a stack of small disadvantages, not a single dramatic curse. It also gives your viewers a nice mental tool. When they hear about a planet that's about the size of Earth but closer to its star, they can think, so, more like Venus then. For thousands of years, people have looked up and loved Venus. It's the evening star, the morning star, the thing that hangs bright and steady when other stars twinkle. You can see it from cities, from deserts, from ships. It's gorgeous, and that makes its real nature even better for a science story, because Venus is a perfect example of how space looks nothing like it is. The reason Venus is so bright is the same reason we can't see its surface in visible light. Its cloud tops are incredibly reflective. Sunlight hits those sulfuric acid clouds and bounces right back. To a telescope that doesn't have radar, Venus is just a smooth, glowing ball. If we were studying our solar system from far away, with only coarse data, we might say, this one is Earth-sized and bright. Maybe a nice thick water cloud atmosphere. But under that white top is a 90-bar blanket of CO2 and an oven-hot surface. That's exactly the kind of trap we're going to face with exoplanets. A planet can look clouded and bright and still be an absolute furnace. A planet can hide an entire climate state under a pretty top layer. Venus taught us that right at home. And it's not just a visual trick. The brightness also fooled us historically. Before we had radar to punch through the clouds, some people imagined Venus as a jungle planet, or a swamp, or a warm ocean world. After all, clouds mean water, right? On Venus, they mean sulfur, and an atmosphere trying to shed energy any way it can. So in your video, you can make that contrast clear. The friendliest looking planet in our night sky is the least friendly rocky planet we have. That's a great reminder that astronomy is always inference. We see light and we deduce the world. Venus warns us not to stop at the first deduction. Venus sits only a bit closer to the Sun than Earth, but that small shift was enough to push it past the point where a rocky planet can keep surface water for the long haul. Before we understood Venus properly, the inner edge of the habitable zone was sometimes drawn almost as a guess. Somewhere inside Earth's orbit it gets too hot. Somewhere outside Mars' orbit it gets too cold. Once we saw that Venus wears a 90-bar carbon dioxide atmosphere and has a surface hot enough to melt lead, we had to admit the line has to be farther out than Venus's orbit, even for a planet very similar to Earth. That's because habitable can't just mean water could exist for a while. It has to mean the planet can get rid of the heat its star gives it. Without boiling its oceans into the sky, Venus fails exactly there. It absorbed more sunlight than it could radiate away. The lower atmosphere got wetter and thicker. Outgoing infrared was blocked, and the surface ran away to a new, hotter state. A planet at Earth's orbit with Earth's water can still balance incoming and outgoing energy. A planet at Venus's orbit with the same tools gets pinned to warm. That realization led to the idea of a Venus zone around stars, a region closer in than the classic habitable zone where Earth-sized planets are likely to look alive in silhouette, but actually be runaway greenhouses. That's important for exoplanet surveys. When we see a small planet close to its star and we can't measure its atmosphere yet, Venus tells us to be cautious. Size is not the promise. Location is not the promise. What matters is whether the planet can hold on to water and whether it has a way to stash carbon. Venus had neither in the end, so the right way to draw the map is to say there is a band outside of which surface water is hopeless, inside of which surface water is doomed, and in between which a planet with Earth's tricks can stay blue for billions of years. Earth sits in that middle band. Venus sits just inside it, on the bad side. Because stars brighten over time, that bad side creeps outward, which means a world that was once safely wet can eventually be pushed into Venus's fate. Venus is just the inner world that hit the wall first, so now it's our marker. Start the green zone farther out than this, or you're lying to yourself about how long liquid water can last. And this is not just a solar system quirk. Around smaller, cooler stars, the habitable zone tucks in close, but those stars can flare harder and strip atmospheres faster, so an inner rocky world there might become a Venus even sooner. That means when we list potentially habitable exoplanets, we have to subtract the ones sitting in their star's Venus zone, even if they are exactly Earth-sized. Venus teaches that habitability is a moving target that depends on stellar age, stellar violence, planetary water, and interior recycling. Without that lesson, we would overcount Earths and undercount Venuses, and we would misunderstand how rare long-lived surface oceans really are. It also tells us something kind about Earth. Our planet has spent more than 4 billion years inside the band where water can stay liquid, even while the sun slowly brightened. That staying power was not luck alone. It was oceans, plate tectonics, and even life helping to draw down carbon. If you took those stabilizers away and left Earth at the same distance, we might have drifted toward a steamy, cloud-wrapped state too. So when we redraw the inner edge because of Venus, we are really circling the thin little strip of orbits where planets can both have water and keep water. Venus sits just below it and shows what happens when you miss. That is why every modern diagram that shows a star and a green ring should, in your mind, have a bright orange warning band inside it labelled Venus Outcome Likely. Our own system put that label at 0.72 AU. We ignore it only if we enjoy being wrong. If Venus is the bad outcome, the obvious question is, why didn't we end up like that? We were made in the same neighbourhood, from the same dust, around the same star. The answer isn't one thing, it's a stack of advantages that all leaned the cooler way. First, distance. Earth simply sits farther out, so from day one we were getting less energy from the sun. That gave us room. Room for the sun to brighten over billions of years. Room for volcanic CO2 to come and go. Room for some water vapor in the sky. Without tipping into the You can't radiate enough heat regime. Venus never had that margin. Second, water, and lots of it early. Once Earth had global oceans, they acted like giant shock absorbers. Water takes a lot of energy to heat up, and it dissolves CO2. So every time Earth got a bit warmer, the oceans could soak up both heat and some of the gas driving the warming. Venus, once it lost its water to the runaway and the sun stripping, lost that cushion forever. Third, plate tectonics. Earth breaks and recycles its crust. That gives us the long carbon silicate cycle, the planet's thermostat. CO2 in the air plus rain plus rock equals carbon locked in minerals, and those minerals get dragged down at subduction zones. Volcanoes then return some CO2, but it's a slow, steady loop. Venus, with what looks like a stagnant lid, can't run that loop. Gas out, not much gas back in. Fourth, shielding. Earth's spinning, convecting core gave us a strong magnetic field, so even when water vapor gets high in the atmosphere, the solar wind can't just tear away the hydrogen the way it could on Venus. That helped us keep our oceans. And then there's the wild card, life. Once life spread over Earth, especially once photosynthesis got going, biology started to help weather rocks, build soils, and even change the composition of the air. That's another soft, slow stabilizer Venus never got to develop. Put them all together and you get two inner rocky planets taking diverging paths. The one closer in ran out of cooling tools first and went into permanent greenhouse. The one farther out had enough tools to keep pulling itself back toward liquid water conditions even as its star grew brighter. The important thing to tell people is that Earth is not safe because of magic. It is safe because several feedbacks are still working. If we lost oceans, or lost tectonics, or sat closer to the sun, we would be telling a story much more like Venus is right now. Venus shows the failure mode. Earth shows the balanced mode. That contrast is the whole reason studying a planet we can't land on for long is still worth it. You'd think we would have explored Venus to death by now. It's close, it's bright, it's a whole planet that went off the rails. But compared to Mars, we barely know it. Most of what we use to talk about Venus today comes from Magellan's radar maps in the early 1990s, from older Soviet Venera and Vega landers that survived an hour or so, and from orbiters like Venus Express that stared at the atmosphere. That's good, but it's not enough to answer the big questions we keep circling. When did Venus lose its water? How often did it resurface? Is it erupting right now? What exactly is in its lower atmosphere, and how is it layered? That's why the next wave of missions, NASA's VERITAS and DAVINCI and ESA's ENVISION, are all pointed at Venus. VERITAS will make much sharper radar maps than Magellan, so we can see smaller volcanic features, tectonic hints, and importantly, look for areas that look very young. DAVINCI will actually plunge through the atmosphere and sniff it on the way down, measuring gases and isotopes that can tell us how much water Venus used to have. ENVISION will do high-resolution imaging and subsurface sounding to figure out how the crust is built. Put together, that's a full set of tools to finally time Venus's fall. Did it boil early when the sun was still faint? Did it hold on a while and then lose it? Did it have one catastrophic resurfacing or several? And because these missions are modern, they can watch Venus over time, look for changes in sulfur dioxide, changes in hotspots, changes in cloud structure, which would be the smoking gun for present-day volcanism. That matters for climate models too. If Venus is still pumping out gas, we know its interior is hot and its atmosphere is still being fed, which means the current state is actively maintained, not just a fossil. If it's quiet, then we're looking at the final, cooled-over remains of a much earlier runaway. Either way, these missions make your videos better. They give you real dates, real numbers, real maps, not just scientists think, and they improve our ability to read other planets. The same instruments and techniques we use to peel back Venus's clouds will be what we use on cloudy exoplanets. Venus is the hard target in the neighborhood. Once we can tell its story cleanly, every other misty rock in the galaxy becomes easier. One of the clearest ways to explain Venus to a normal person is to say, it's Earth on hard mode. Take our planet, remove a bit of distance from the sun so everything starts warmer. Spin it so slowly that the atmosphere can dominate day-night differences. Give it no strong magnetic field so the top of the atmosphere is more exposed. Let it lose most of its water so there's no rain or oceans to wash CO2 out of the air. Don't give it plate tectonics so there's no long-term carbon burial. Then let the interior keep erupting so gases keep being added. If you do all of that, you get a world that cannot help but run into a permanent greenhouse. Venus shows us that you don't need exotic chemistry or a bizarre star to break a planet. You just need to stack small disadvantages until the feedbacks all point the same way. And once they point that way, everything the planet does afterward reinforces the hot state. Volcanism, more gas. Sun brightens, more heat trapped. No water, no weathering, no plates, no burial. Thick atmosphere, no cooling at night. Slow rotation, air can smear the heat around. The planet is doing normal, boring planetary things, but in Venus's configuration, those normal things become a trap. That's valuable because it kills the lazy assumption that rocky planets always self-correct. They don't. Earth looks self-correcting because it still has its water, still has its plates, and still sits far enough out. Venus proves there is a regime where self-correction stops and self-reinforcement starts. That's the regime we should expect for many inner rocky exoplanets, especially around stars that flare or brighten faster. So the slogan version for your viewers is, Earth is what happens when all the stabilizers are on. Venus is what happens when you turn too many of them off. Same basic hardware, different settings, wildly different climate. When we talk about Earth's far future, we can picture a long, slow fade. The sun keeps getting brighter. Our oceans slowly evaporate. Plate tectonics might slow. Life retreats to the last wet or shaded places. And billions of years from now, Earth finally becomes uninhabitable. Venus has no such gentle path. It is already in the end state that inner rocky planets are expected to reach when their stars brighten. Hot, dry, thick atmosphere, no oceans, no big sinks. As the sun continues to brighten over the next billion, 2 billion, 3 billion years, Venus will simply stay awful. There are no seas to lose, no ice caps to melt, no big climate shifts waiting. Its atmosphere will probably keep being eroded at the top and perhaps topped up from below, but the surface is going to stay at melt-your-lander levels. Then, when the sun eventually swells into a red giant in about 5 billion years, Venus will be so deep in the danger zone that it will either be stripped, baked even harder, or swallowed. In other words, Venus is already where Earth will eventually go, and it has nowhere else to go. That's a really clean point to make in a sleepy science video. Some planets still have choices. Venus used up its choices a long time ago. That also tells us something about inner planetary systems in general. If you look at an old star and you see a hot, rocky planet close in, there's a good chance it's in a Venus-like terminal state. It isn't on its way back to blue. It isn't waiting to regrow oceans. It's just going to sit and cook until the star decides to finish it. Venus lets us look at that future without waiting billions of years. We can see the end game now. Because Venus is such a nasty place for hardware, most of what we will ever know about it will come from short landings, brief atmospheric dives, and a lot of careful radar and spectroscopy from orbit. That means the knowledge is fragile. It lives in maps, in gas profiles, in odd little signals that tell us sulfur dioxide went up one year and down the next. If we want future scientists, or future humans who are living around other stars, to understand how easy it is for a rocky planet to ruin itself, we have to save Venus's data as carefully as we save moon rocks and Mars cores. Venus is our only nearby confirmed case of a runaway greenhouse on an Earth-sized planet. If we lost that record, we'd lose the most convincing evidence that too much star plus lost water plus no recycling equals permanent hell. Archiving Venus is archiving a failure mode. That's valuable in engineering and in planet science. When you build bridges, you keep the reports on the ones that collapsed. When you build climate models, you keep the data on the planet that cooked. And because exoplanet astronomy is just getting started, the better we know Venus now, the better we can interpret the cloudy, low-resolution signals we get from worlds around other stars. So part of Venus's story is really about us. Will we be smart enough to save the map of how a planet breaks, so no one has to rediscover it the hard way? So we can finally say it all in one slow breath. Two rocky worlds were born beside each other in the sun's inner disk. Both were wrapped in the same raw materials. Both were struck and melted and sorted into core and mantle. Both breathed out early atmospheres. One stopped a little farther out, gathered and kept deep oceans, broke its crust into moving plates, built a magnetic shield, and eventually sprouted life that helped it keep its air balanced. The other stopped a little closer in. That small difference let more sunlight in, warmed its young surface more, and made it easier for water to sit in the sky. As the sun brightened, the closer world slipped over the line. Water vapor thickened the greenhouse. The planet couldn't radiate enough heat. The oceans, if they were there, boiled into the air. High up, the sun split that water and stole the light part, so the cooling tool was gone for good. Volcanism kept talking, but with no ocean and no plates, every word of CO2 stayed in the air. The atmosphere grew heavy, fast, and hot. The clouds turned to acid, the winds wrapped the planet, and the surface was locked in a state it could never climb out of. From far away it still looks perfect, bright, round, steady. Up close it is pure consequence. And that really is why Venus belongs on your channel. It proves that rocky planets do not all get happy endings, that being like Earth at birth is not enough, and that small orbital differences can, over billions of years, turn into total climate divergence. We live on the one that kept its water and its drains. She is the one that didn't. Thank you for listening to her story. Sleep well, and be glad we orbit where we do.